So we are going to do a problem with the Riemann sum where we're given a particular function here. I've chosen x times the square root of x cubed plus 8, and we're going to approximate the area under this curve with left endpoints, right endpoints, and midpoints. So I can draw the picture over here. Not that it's terribly helpful to us, but maybe it's like helpful enough. It looks something like this. Yeah. Right? At 1, right, we're already over here. So anyhow, this goes up really high, but I'm looking at an area sort of like this. This would be 1 and this would be 5, right? You can see at 5, this is pretty big. So essentially, what I want to do though, less concerned with what the picture looks like than what my interval is and what my partitions are going to be, right? Because I'm going to do, say, L8 first, left endpoints. So I'm going to have my sum going 1 to n f of some xi, well, fine, we'll call it, this is the 8th. No, that would be the right one. Well, it's fine, but we'll do it this way, right? Let's do XL because it's the left endpoint. How about that? And now these are my intervals on my subintervals, right? I've got 8 subintervals. So what's delta x first of all? Delta x is b minus a over n, right? That's 1/2. Of course, that makes sense. I chose it so it's not too hard. I've got an interval of length 4 and I'm dividing it up into 8. So obviously I'm going to have intervals of 1/2. So let me just kind of draw this. I do find it useful to draw my partition when I'm doing these, especially because I'm going to write down what it is. So this would be 1, 2, 3, 4, and then what is this? 3 halves, 5 halves, 7 halves, and 9 halves, and those are my sub-intervals for my problem. So really and each time my delta x is going to be 1/2. So really what this is and I'm going to now do the left endpoint. So for each of these little intervals, I'm going to start from the left. So I'm going to have f of 1 times 1/2 plus f of 3 halves times 1/2. And all of these, I'm going to write it out so that we get an idea of what we're doing. Again, you're going to have to, when you do this, okay, I do admit it's a pain. I do not love it myself because f of 7 halves times 1/2 plus f of 4 times 1/2 plus f of 9 halves times 1/2. Now I stop there. I don't put an f of 5. Why? Because I already took care of this. I'm expected to have 8 terms because I have 8 subintervals. 1, 2, 3, 4, 5, 6, and 8, right? Each one of these then, I have to take this and plug it into here to get the number, add up all those things. Your calculator, probably there's a way your calculator can do it. I'm not great with calculators, so I don't know. I just kind of did it myself, but and I know the GeoGebra worksheet does it too if you are needing. 74.833 is what the number that we got. Now if we kind of just sort of look at this, I'm not going to draw 8 rectangles here because they'd be too small. Even 4 rectangles is pushing my drawing ability, but you can see from the left endpoint it's going to be an underestimate. So because this function is increasing, my left endpoint is going to be the smallest possible. So I'm just going to keep this here. So for my left endpoint, my number is 74.833. Now I'm going to do the same thing with the right endpoint. So, and I'm evaluating this yes, it means each time plugging each of these numbers into this f of x and figuring all that out and remembering to divide by 1/2 in the end. There's going to be 1/2 on each one, right? My right endpoint is going to be kind of the same deal, right? I've got R8 f of x r delta x. So yeah, I'm going to have a 1/2 and everything, so maybe I'll just write it like with the 1/2 in front here. So my right endpoint, though, I'm going to start with the 3/2 and I'm going to end with the 5. So it would be f of 3/2 plus f of 2 . And then when you calculate all that out, this is 102.65. Okay? So again, now this one is going to be an overshoot, because if I do the right endpoint, you can see it's going to be over. In fact, so this is significantly under, and this one is actually significantly over, even for the 8 rectangles. But now the last question was about the midpoints. So for the midpoints, it's a little bit more work because I have to go back to my intervals and figure out the midpoint of each interval, but luckily, of course, we chose something that isn't too hard, right? So it's easy enough just to look at this and figure out, okay, what is the here? This is going to be 5/4, then 7/4, and you just kind of figure out what those midpoints are. Of course, you can use the midpoint formula, or you can just sort of figure it out. 15, 16, 17 fourths, 18, no, 19 fourths there, right? Because then 20 fourths would be 5. Okay, so those are the midpoints of my intervals. So if I'm going to go through here, let me do this. My right endpoint gave me the number 102.65. And then if I'm going to do my midpoint, I'm going to evaluate, and this is the same deal, right? It's going to look just like this, but I'm going to evaluate it at each midpoint of each interval. So my first is going to be 5/4, my next is going to be 7/4, etc. So in terms of making this a little less onerous, especially in terms of maybe on a test or whatever, do try to look up with your calculator. Any of your graphing calculators should be programmable to the point where you should be able to just program it to do this so that you're not having to punch that in every time. But again, don't ask me for help because I don't know. Anyway, if you evaluate this midpoint, the midpoint form, I'll just write it here, ends up being 87.74. And if we actually calculate the area with calculus techniques, though that is not nice, it's not good, easy to do at all there. It's not an easy integral, but it's around like 88 or 89, I think. I can't remember exactly. But this is very close, whereas both of these were significantly farther. So even though it's a little bit of more pain to find the midpoints than it is just to use the left endpoint or the right endpoint, we got a significantly closer answer to our integral. To our area.